Hi everyone, and welcome to today's session. So today will be a continuation of what we did last week. So I'm going to talk about a roadmap for AI. Last week, we talked more about the past and the present, which is like how we have expert systems that use fixed rules that are codified from experts, and how we instead go over to data-driven kind of rules where we use things like neural networks using supervised learning to try to identify a set of relation between the input-output data. Okay. Eventually, we move over to unsupervised or self-supervised learning, whereby we don't even need human labels. We just let the data learn on its own using tasks like next token prediction. So this has been very successful. And now with more and more data, we are creating larger and larger foundational models that leverage internet scale data in order to boost the system's performance. So how then do we move from here? So this is exactly what we are going to talk about today. Like we're going to talk about how we're going to move beyond these things. But first, a recap. So expert systems, as what I mentioned earlier, we use the human experts to codify the rules, things like decision trees or those kind of rule-based systems like if-else systems to kind of decide what's the outcome. Supervised learning does away with the expert rules. Instead, we learn through input-output relations using human-labeled data, like for example, a classifier of dogs and cats using a neural network. And lastly, the unsupervised learning framework uses things like next token prediction, like in a transformer. So having said all this, right, what's next? So before I move on to what's next, I like to highlight that all these three systems are not in isolation. Actually, there's a lot of interaction between like expert systems, supervised learning, and unsupervised. Okay, I mean, there's a lot of ideas that are used from one system to another. And so now we are in the era of unsupervised learning or self-supervised learning because of ChatGPT or large language models, proven quite capable. You train on the next token prediction task, you can do so many different things like translation, summarization, and so on. Okay, but do we really want everything to be like free flow, like you don't have any more like pre-processing steps or fixed structure? Not really. Okay, in the era of like end-to-end kind of learning, like unsupervised learning, I would like to just give a caveat that fixed structure is still quite important. Okay, why? Right. Firstly, if we try to learn everything about the world, all the information that you have about the world, you try to learn wholesale, there will be a problem. Okay, there's just too many ways to learn. Right? If you know the information theory concepts, if there's like many ways to fit the data, like okay, for example, ignore the diagrams for now, just take a look at this chart here. All right. These are your data points. X are your data points. X and Y axis doesn't really matter. Okay, what are the ways to fit this X? Anyone can tell me like how can you fit a trend? Like if you want to draw a regression line, like how can you fit it? Okay, so maybe one way is to fit like one line like that. All right, one straight line. Another way is to fit like this. Then another way is to fit like this. I don't know whether you have seen lines that look like this, but there's many ways to fit the data, and if you let full end-to-end learning take place, all three possibilities here are possible. Like which one should you use, right? So the way we can make learning faster and you can learn from like fewer samples is not to do full end-to-end learning. Actually, we kind of still want some structural bias. Okay, some structural bias can help to ground the kind of things that we can learn from the data. Like for example, if I say that I can only fit a straight line to this graph, immediately this purple line, okay, will be the one selected, and we will learn the simplest relation. All right. So what are some of the things that we can help to speed up learning? Okay, for example, in convolutional neural networks, this thing called filters are used, and these filters help to basically ground how we view each patch of the image. So by doing a convolution over this image patch, right, and this kernel is always fixed, okay, we get translational equivariance or invariance where you can use the same, like if let's say this patch is to find out a dog's face, we can apply this dog's face patch to every single part of the image. And this helps it to learn faster because you just need to learn one patch and then you can apply every single place. Okay, rather than learning one by one at each location, which is what the vision transformers are doing. Okay, so structural bias is important. That's also why you see like ConvNet's learning much faster than vision transformers. Okay, structural bias will be able to help us to learn faster in the age of end-to-end learning. Okay, I don't think full end-to-end learning is good. Okay, because of what I mentioned earlier. Right, another way you see structural bias is token embeddings. Okay, we don't just arbitrarily encode tokens, we split by subwords, and these subwords have some meaning, like for example, walk, and then ing, walking, instead of you split by letters. If you split by letters, like walk, walking, you don't get much meaning in this different characters. But if you split by walk, you can have an embedding space, okay, for your token here, which characterize the kind of movement of walk. And then if you do like walking, or you do other things like run, maybe walk and run could be quite similar in the semantic space. So this structural bias comes from how we tokenize. It's not perfect right now. We use bytepad encoding, which uses statistical properties of letters together, of characters together. We group more common characters together in bytepad encoding. Okay, but the idea of having some structure helps to ground learning. And this is what you see in large language models as well with token embeddings. Okay, sorry, token embeddings are here. Okay, this bird uses segment embeddings as well. Okay, I just showed this diagram here because I just want you to see like how the tokens could look like. Okay, like here, my dog is cute, then the separation, all these are tokens. Okay, so if we don't have this structure, we will take much longer to learn this meaning. And a lot of pre-processing steps that are used in supervised, unsupervised learning systems actually come from some form of expert systems. Like, for example, stemming, tokenization, like those NLP techniques is basically carried over from how expert systems but used to do it in the past, like those rule-based systems. Like, so we actually can get some form of structure grounding using prior knowledge that humans have already extracted from the data, and you don't have to relearn those. Okay, it's like DeepMind always likes to say, we can do full end-to-end learning. We learn everything from scratch. AlphaGo, we try to do away. AlphaZero, we do away with human intuition and structure. Yes, in some cases, those help us to get optimal spaces in the world because humans are not exactly optimal. Okay? But in most cases, if we were to learn end-to-end, we will take forever to learn. Okay? So some structural bias would help to ground it. And I think this is very, very important moving ahead because I think our systems should have some form of grounding in order to learn faster. Any questions so far on this slide? Okay, so another thing I would like to add for grounding is this thing of rule-based as well. So in this era of unsupervised or self-supervised learning, should we just throw away everything we have done in the past? Like all the traditional expert systems or like supervised learning methods that perhaps, okay, maybe not supervised learning, but maybe should we throw away expert systems altogether? All right, so let's take a look at like ChatGPT right now. Okay, right now ChatGPT, you can do zero-shot, few-shot prompting. Okay, if we were to use, okay, let's say a rule-based program is something like a programming language. Okay, you need to program a programming language extensively. It needs to be very defined, well-defined functions, well-defined commands to the programming language. But with GPT, you can perhaps, do away with the programming language. You can just say you are sentiment analysis bot, or you are a trading bot. You can say stuff like this, and hopefully you cross your fingers. Hopefully it will work. It doesn't work most of the time because it's not very consistent. Okay, so this is the second point. The first LMs, they are stochastic in nature in the next token generation. Okay, even if you set temperature 0, okay, you just change the prompt a bit, the output might be different already. All right, for the same stuff. You just say you are a sentiment analysis bot or you are a bot doing sentiment analysis. You just change the sentence a bit, maybe you get different output. Okay, but for code, okay, the moment you code it in, the performance will always be the same because it's a very fixed language, right? So the other thing is ChatGPT is able to do intent processing well, like you are sentiment analysis bot. But this programming language, you can't, okay? You can only do what's programmed. Okay, so why am I talking about this? Is because I'm saying that in the age of unsupervised or self-supervised learning, we actually kind of still need this part here, this rule-based part here. Like LMs cannot do math well, programs can do math well because they are consistent. Okay, they can calculate numbers well. The LMs cannot do rule-based checking well. Like for example, you want to check whether a number is greater than 100 or something like that. Okay, ChatGPT is not very good at it, but rule-based systems can do it. So I believe a hybrid is very important, it's necessary, because if we just do full unsupervised learning, especially unsupervised learning that is black box based, like you don't really know what's going on in the attention mechanism, okay, you may end up with cases whereby it's just not doing the right job, okay, because LLMs are not meant to follow rules strictly. So I'm saying you should use both systems. And this is very important when we talk about the agents later. Okay, when you use LLM-based agents, we kind of still want this kind of rule-based things to be present because of such characteristics. So that's it for this slide. So now let's talk about something that I feel most strongly about, memory. So I believe that the current neural networks paradigm is slow to learn. It's quite good if you have a lot of data and a lot of time to learn from. Okay, but if you want to do adaptive learning, online learning on your new set of data is not sufficient. We kind of still need some form of memory. So these are some examples of how large language models can actually use memory to learn fast. Okay, large language models are trained on a large corpus of data using unsupervised learning during pre-training step. But during inference, you can just zero shot from them to say you are a sentiment analysis tool. Okay, if it's very in distribution. Okay, if the stuff you want them to do is something out of distribution, like to do decision making for some environment that he has never seen before. Okay, maybe you can ground it in some examples. Okay, this is called in-context learning using few shot prompting. It may not be useful if it's too difficult for the LM to learn. If the task is too difficult, it must be very similar, again, quite similar to the training distribution. But this means that some form of memory, okay, in the form of context prompting, can actually help the LM do a diverse set of behaviors, and which is quite useful. This highlights how versatile memory can be. Okay, you can also prompt it sequentially, like let's think step by step, in order to ask it to think, like for math problems, how to calculate step 1, then step 2, then step 3. Or if you can do broad to specific prompting, this is also a way to ground your memory. Like for example, you want to ask it to come up with a country first, then you ask it to come up with like a city, then ask it to come up with a job, then ask it to come up with a description for the job. So something like this, if you already know what you want to come up with, you can ask it to do a broad to specific kind of prompting so that whatever it comes up with at the bottom, it has these things as context. So this is exactly what memory can help us with. You don't have to learn everything using backpropagation. All you need to do is to just give it some form of condition using context. You use memory as a way to condition your generation. You can get very different generation that is suited for what your context is. So this is actually very powerful. And LLMs have highlighted that this memory component is super useful. I really like to thank LLMs for showcasing this, because this thing is not evident. Everyone used to think neural networks are enough. But with LLM, suddenly we use memory prompting, context-based prompting. And that kind of changed the whole viewpoint of the field altogether. So one very, very interesting thing is retrieval augmented generation, where you just use like maybe cosine similarity to retrieve relevant context to your query. If, like, for example, if your query is what can OpenAI do? Okay, then your context, maybe you can talk about like OpenAI now has GPTs, you can have agent behavior, that kind of thing. So before that, maybe I don't know about this because this just came out today in OpenAI dev, okay? But you as cheaper GPT inference, something like that. Okay, you can use the context retrieve it. Okay, so this thing here is also known as memory, and this can be updated dynamically. So today I know about OpenAI announcement, and I can update all this context already in my database. And when I query this, I can immediately use cosine similarity or some similarity metric to retrieve out the relevant context here. And then my output generated will be related to the context, or will be grounded to the context. Can you see how versatile this is? Okay, I only knew of the information today, and yet my rack can already have this data and can use this data for my generation. Okay, this is very useful, especially for agentic behavior. When you want the agent to learn from data, learn from experience, you can use rack directly. As long as you have a dynamic memory bank, you can use this to learn immediately from the environment change. Okay, questions so far on this? Okay, I think all of you are very familiar with this. So one very interesting thing that is quite popular nowadays, okay, is knowledge graphs. Okay, is back. You see, rule-based systems are back again. Okay, why knowledge graphs? Okay, knowledge graphs are able to express things in like a very structured form. Like you have a certain entity and a relation and an entity. So for example, the entity could be like John, and then like you can say the relation is like attribute. You can say that John is tall. Okay, I mean I'm not tall, but I'm just saying that you can express a knowledge graph like that. And this basically can embody structure in the data. It's accurate because you store this in a fixed structure that is not you don't hallucinate this structure. This structure is derived from your data. Okay, you can interpret it, you can incorporate your domain specific knowledge and so on. You can actually make this into a sentence. John is tall later on. And this can be the context. And people have found that you can use this to put maybe like as retrieval augmented generation can put inside your LLM as your context. And this improves the generation capabilities of your large language model. Because right now, instead of having your context as just one database, you can have your context as maybe this kind of entities here, and you can retrieve the right subgraphs and so on. Right. So this has been used like by software systems such as like Neo4j, where you can query over the knowledge graph, extract out the right portions. And then the next step is you can just put into the large language model, right? Large language models can also help with generating this kind of attributes, like this, can generate this using some prompting. You can do few shot prompting of what entities you want, what relations you want, using your respective ontology of how to get your entities and your relations. So it's quite useful, and this allows the large language model to be grounded in some source of truth, which is from the knowledge graph. Right. So I was very impressed with this. Okay, until I tried it out. Okay, actually it turns out that this step here of using large language models to get the knowledge graph, this is actually hard to do. Okay, why is it hard to do? Okay, because there's so many different ontologies you can extract. Like if the text is like John is tall, then you can attribute like that. What if the text is like John is tall, but John is tall in May, but taller in June. Okay, how are you going to represent this, right? so I mean, what will end up happening is something like this. You have something like here. John is tall in May. So yeah, sorry. Anyone to say something? You might end up with something like that, and then you have May over here, and John is taller in June. Yeah. So with a very versatile way of expressing your knowledge graph like that, it's actually harder to interpret if you look at this. Okay, maybe let's do a show of hands. Who here thinks that the knowledge graph encoding of this sentence is easier to read? Anyone? Okay, who here thinks this sentence is easier to read? You can raise your hand. Okay, thanks, Richard. Yeah, so this is exactly what I found when I actually tried to do this knowledge graph kind of prompting it. The ontology itself can be very restrictive. It can make you generate the knowledge graph that is actually harder to read. Sorry, Volodymyr, you say definitely easier is what? The knowledge graph is easier to read or the sentence is easier to read? The sentence, yes, correct. So one thing I realized is that if we encode out the sentences into a knowledge graph, we might actually lose our information. And also when we retrieve this knowledge graph, we might actually retrieve it in a way that is different from the original meaning of the text. Because there are some nuances in the text that may be lost if you if you kind of encode it in a structure like that. Yeah, and also like I start to think, in the brain, do we actually form our knowledge graph? Do I have like an attribute like associated with every person? Like for example, if I have a friend named Mary, do I attribute Mary with like intelligent, um, likes red color? Do I have this kind of like very, very structured kind of relation with associated with that person, Mary? I started to think about it and kind of doesn't feel right because I don't have this list readily available. I have to imagine my friend Mary. Yeah, I don't have this real friend. I'm just saying an example. I had to imagine my friend Mary, and I have to start thinking, okay, how does she look like? How does she normally behave? How does she dress? So all this episodic memory will come in, and then I will infer these characteristics from referring to that memory. And with a few friends at my Discord group, especially Richard, I start to think that maybe we could have a more flexible knowledge graph. Okay, and this knowledge graph is what I term the chain of memories. And if you look at this chain of memories here, is basically saying that we don't have a fixed ontology to extract out all this data. We can just store the whole chunk of text in this memory. Okay, or whatever stimuli. Next time you have images and so on, audio, you can store the whole thing in this memory. Right? You might split up the memory into sub portions, sure, but you don't have to have the memory form any relation with each other. Okay, this is the crucial part. If we want to access a query, okay, if let's say we have a query, okay, by the way, whatever you are listening here is all very cutting edge ideas, okay, it's not even published, it's just new ideas that were gotten because of the limitations of existing ideas. Okay, so let's say if you have a query over here, all right, and the query is something like, where should I eat ramen? Okay, let's say I'm very hungry, I want to eat ramen right now. So actually all your memories of the past, you could have a memory A that's talking about you eating Japanese curry at mall X, okay? But then that's not the only thing in your memory, okay? The memory actually is very, very diverse, okay? Also has 100 plus other facts, actually much more, okay? Or other information, okay? So that's memory A, and then we have memory B, okay? Memory B is talking about like eating steak at a steakhouse at mall Y or at I don't know, at island Y, all right, plus 1,000 other information. Okay, let me just put this somewhere else. Okay, so you can see that this memory itself contains a lot more things. And if you were to extract it out in the knowledge graph straight away when you store it, you might lose out all this other information. So we try to delay the extracting out of structure until the latest possible moment. Why not we just store the whole memory first? All right. And then what we do next is based on the context. Okay, like where should I eat ramen? All right. We can perhaps query, like query key value kind of thing. You can query the relevant parts of the memory. And then like Japanese might be queried based on the query key value. So this is the attention method. Attention query key match. Yeah, then you can use like cosine similarity between vector embeddings to do that. So it's very similar to current methods, but you can find the memory based on like a query key embedding of like the query to your memory. Of course, there are various ways to improve the accuracy of the search for this. I'm not going to cover that. But the idea is you keep your whole chunk of memory there. Okay, or you can split into smaller chunks, of course. Okay, and you find the memory you need. Okay, and this is not all. Okay, this is actually quite similar to current methods. But what can be done next, okay, is that after you extract out maybe certain memories, okay, you realize that, okay, maybe I don't have all the information I need. It's like, okay, I have a memory of eating Japanese curry, but I was thinking whether I should eat ramen. So maybe what you can do is you can like maybe ask yourself like, okay, I don't seem to have many memories of ramen. Okay, maybe like my updated query can be like, do I like which place? Okay, so instead of like asking for ramen now, maybe I can look at Japanese food place. Maybe that will give me an answer. So I form an initial gauge of the situation first with my first memory, and then maybe that's memory one. Okay, then I want to find out like what's next? Okay, then I will jump using an updated query. I will jump to the next memory and so on. So the memories itself, they don't have a link to each other. But for example, if you want to talk about ramen, maybe the red color link is about Japanese food. And the green color link here is maybe about Western food. Okay, so we just keep jumping around in this memory soup, and eventually we'll get our answer. Okay, I don't have a full description of how to like really implement this out yet, because how to get all these memory chunks here is an open question. What I was thinking is maybe we can store them at various abstraction spaces. You can store like the whole chunk, you can store the sentence level, you can store multiple sentences and so on. Doesn't really matter. In the end, everything will be all in one soup, and you just keep jumping around the soup until you get your answer, right? And you do your inference all on the fly. So this is a new concept. And I think in order to do this, you will need to form context-dependent embeddings. Okay, and this context-dependent embeddings is something like this. Like you have this query here. So when we do our cosine similarity, it should be based on ramen, which is like Japanese food and so on. So we need to extract out stuff that are similar to this. And I'm not too sure whether cosine similarity can do the full context-dependent embeddings. There may be other ways to, do some form of like, maybe in your context, you could do like Japanese food, and then you do query, where should I eat ramen? So that's one of them. All right, so this is the context-dependent query. Okay, of course, if you could just do the context straight away, that would be great. All right, then maybe you could have like context Japanese food, and then you can have like memory A description. So if there's a way to prime your memory based on a certain context, maybe you could have context-dependent embeddings, which then you can use to jump from one memory to another. Yeah, so that's some of my initial thoughts. Okay, and I think if we can do something like this, okay, maybe we have to retrain another model that takes into account context, apart from just the two sentences or two of query or key. If we can have another context to condition on it, okay, I think you will find much more relevant memories that are based on the context, and you can form these dynamic links on the fly. Okay, so Kai asks, so what you are saying is the ages are dynamic? Yes. There's no static ontology like a standard knowledge graph. The ages are constructed based on your context. Based on your context, like for example, in this ramen, what will happen is that we will form links, okay, between similar memories based on that. And actually, these links, you don't even need to form it. You can just go through your entire set of data and do a cosine similarity, which is just one for loop, actually. It's very fast. Okay, but the key idea is that it must be context dependent. You must condition your embeddings on the context that is relevant, because one memory can have more than one thing. You could have Japanese curry, you could have like you went to see the Christmas tree lights. All these are not relevant. Okay, we just want the relevant parts, which is the Japanese food. So this context here can help to ground the embeddings to a suitable space. Okay, but of course, if the original cosine similarity can work already without doing this context, sure, that works too. Okay, then what will happen is that we will just need all these memories in a soup. Okay, we don't need ontology at all. So at least this is a new kind of idea that I'm thinking of. And yeah, happy to hear some comments or discussion on this. Yeah, maybe we just stay here for 1 minute if you have anything else you want to add for this.
Oh, I was just thinking, as we look at this and you're talking through, say, this example of you go out for a meal and there's Christmas lights there, right? Now, clearly these are not, like, if you've been in that, and I have a place in my mind, London Regent Street, whatever. Great. That's what Christmas lights mean to me, and probably meals and beers and whatnot. But it doesn't affect where I'm going to go and get something to eat, right? That's not relevant to that train of thought, but it's definitely associated. And I think the challenge is to find, there's a question saying, what are these edges in the graph, right? And I think that's an interesting point. So you've got when I was toying with this in my head, there were literal edges with a weight on them, just a weighted graph, right? But for no particular reason in my head, right? It just whatever we associate And it's built up in the same way as embeddings, right? The more times you make the association, the stronger the weighting, maybe, right? But also on the other hand, there's other types of relationship, particularly temporal, right? So we were talking about, or temporal, whatever, in time. So these things happen at the same time, so they're relevant to each other, even though they have no specific other association, like your Christmas lights as you eat a meal, right? Which is associated perhaps to meeting some friends or playing with kids or something, right? So trying to find those associations in place and in time and other things, they're these sort of this metadata which is relevant and makes the relationship, right? And I think we and we talked previously on Discord sometimes about the role of emotion as well. So you have these sort of all these bits of metadata that come together for people to make associations to times, places, memories, and so on, right? And so I'm trying to think of how to. I was keeping them in my head, this abstract number, because that's a thing we can. I'm looking to how to build it, right? And that's just how I approach problems. And I know a weighted graph is a thing, and it's lots of well understood maths to go with it. But that doesn't address all those other data structures there might be. Right? So when you were talking about earlier about Neo4j and about ontology and so on, and what I was thinking about with other styles of database, like time series databases. So one is a ontological relationship, which is graph form, but there's also a temporal relationship, which is log formed, right? And so we're going to say log means strictly A, B, C, D in order, right? And then there's other things like some movies that mess around with narrative order, like I think what was the reference? I think Reservoir Dogs maybe, where they just chop out a whole bit of the middle of the movie. That's a different Tarantino one. Anyway, Bruce Willis and friends. So but they mess up the timeline deliberately to change the way you experience it, and it's up to you afterwards to figure out how it originally fit together. So time is quite malleable, but it's strictly speaking, your experience of it is log structured, right? A before B before C before D. But if you went and saw it at a cinema movie, which cinema, quite likely. You can probably guess where you were sitting in the cinema. It didn't really change your experience of the movie, strictly speaking, but it's all there. And maybe you saw that in the same cinema for some other movie you liked or remember particularly well. But when I'm trying to figure out, so when we discussed this on Discord, there was a bit of, and I was saying like there's all this fluff and ephemera that comes with our memories, right? But
yep.
In my head, we need to have some kind of tidying. Like in our brains, that happens when we sleep, right? And the one theory goes, dreams are just the bits you've cut off from your other memories, and they're just swimming around in your head while you're sleeping. And when you wake up refreshed, and your brain's a little bit better organized with a bit of luck, right? So I think there's these challenges around, like I favor personally a loose representation, but then the trick is deriving relevance because it's loose, right? Each relationship doesn't mean very much. Whereas if you go with a really strict representation, a tight ontology, like a knowledge graph, then relationships are easy, right? Relevance is really easy because it's all the hard work's already been done. And I think for me, I guess that a combination of a directed graph, a weighted graph, and and possibly directed as well. It's a whole other thing, right? But and possibly but necessarily probably some kind of tidying, garbage collecting kind of idea has to happen on an episodic basis, because otherwise it'll just be, it won't be a soup, it'll be a flood or a tidal wave.
Yeah.
Yeah.
Maybe that's where the attention mechanism comes in. Like if you already know the stuff, you don't store them as new memories. But if you don't know, then you will be curious and you pay more attention, then you encode new memories. Yeah, maybe that's where and emotions play a part as well. If you are surprised, because something has changed in the world, you basically form a stronger memory. And
I think so. Yeah.
I do think emotions play a huge role here, at least for an actual agent. Like, and I quite like the part that you mentioned about time, temporal aspects, because indeed, when we kind of rummage through our memories, we kind of associate them with like the time as well. Like, for example, if you start to imagine yourself watching a movie, you start from the beginning and you go to the end. Okay, maybe you stop halfway, but you will essentially like play out the episode again, and this kind of helps to help us think through. Then in the middle, if you have some like revelation, hey, or let's say it's the movie Harry Potter, then oh, what books have I read? Then you'll go back to your memory of you reading the books and so on. So definitely the temporal aspect would help us to find out more about how the memories work and how they link to each other, because memories encoded at a specific time, like multimodal memories, like vision, audio, touch, all this are all linked together. Like if I see my old school, the memories of me hearing some music there might come up, or like if I hear the music, I might think of the school. This are all interlinked. So let me add this point here: multimodal characteristics are all learned from same memory. So I believe the entire memory is multimodal. Okay, whether is it encoded in the same place or not doesn't really matter. The main thing is once you think of one, you think of the rest. Okay, the connections in one mode to another based on just this time or place is very strong. Place is also very strong in here. So like we also encode memories quite strongly on using the place of where we store the information.
Yeah.
Yeah.
I think we mentioned once about this idea of the sort of memory technique of a memory palace, or
Yeah,
an
memory
imaginary
palace.
filing system, and that seems to be, like, historically a very effective way to remember stuff. Association, even if it's not a real place, even if you invent a place, it's a very efficient way to make memory associations. Like, it seems our memories are very bad at storing ideas without relationships. And something relatively concrete, even if it's not actually literal concrete, then that seems to be a very useful association. I think that's an evolutionary thing. Like, we needed to find wet water and food and stuff like that. But before we were humans, we had these problems of knowing where to find stuff. And so I think there's a bit of that going on. Like, the place is definitely a big memory key for us. Emotion, I think, goes with it, and sensory inputs. Those are like those are back in the lizard brain, somewhere in your brain stem is where those ideas live. Way back before we developed, logic and other crazy stuff.
Yeah, very interesting. I just wonder also whether the context could be like context by place, context by time. Maybe you can filter out everything except place. I'm just thinking that the way this memory linkages work could be like conditioned on some aspects which perform like a filter. Like if it's a place, you only think of those particular places. A time, think of that particular time. Maybe those are like aspects of memory that are stored. So when you think of that memory, you more strongly want to take things that are in the similar place or time. Okay, but at the same time, you can also take other memories. It's just that this place or time memories are so strong, you will tend to take them first. So maybe that's why we tend to think that, okay, our memories are indexed by place or indexed by time. Maybe there's no index at all. Maybe it's just the way it's encoded. It makes the relation very strong for memories of a similar place and time. Like what you say is like the whitened graph. I mean, it has very, very strong connection there, but that doesn't mean that it has no connections to the rest of your memories as well. Yeah. So, I mean, because if you think about it, like right now, if I talk about like chain of memories, okay, you might think of the word chain. Okay, it's nothing to do with time nor place. Okay, it's just by analogy, like chain as in metal chain and so on. So there might be relations of various forms, but time and place might be the strongest. What do you think about it?
Yeah, I'm not sure the strongest, but I mean, I think it depends on, like, it's needing a steak. And for me, I have a recollection of this place in London did an amazing steak, cost a fortune. Somebody else was paying. It was great. But it was, and I can tell you where it was, but it was nearly 20 years ago. And I can't tell you which day it was. But I can tell you that it melted in my mouth and it tasted great, right? And a whole bunch of other stuff about that evening, but I can't really tell you when. I know I can do the maths and go, it's about 20 years ago. But the further back it is, the less strong that association to time is, right? Because people start mixing up, like, there's one of the things that people start mixing up the order that things happened. Like, if you look into studies of eyewitnesses in criminal cases, and they're notoriously unreliable. People have terrible memories. They make stuff up all the time. and a skilled questioner can create memories in a witness that didn't exist in the first place. Right? This is all really, like, in psychology literature, it's really well documented. So memory is not, like you were saying once about LLMs, they don't have facts, they have opinions, right? And so that's why it's quite hard to remove some facts from an LLM, right? Because it doesn't work like that. It's not.
I actually don't even think LLM store facts. What they are doing is storing correlations. Facts.
Yeah. That's what I mean. It's
interpreted. They're just
stochastic.
interpreted by humans. Yeah, like what is actually a fact? We also don't know what is a fact. It's just agreed upon by humans that yes, okay, the sun rises in the east. You know that can be just a chain of correlations of probabilities of next token that just matches what people normally think. But what is a fact? I don't even think humans know what is a fact. As in, that is really based on collective knowledge and so on. Facts can even change, like science is not fixed. So yeah, I don't think we need to talk about facts here because facts is just a human way of viewing things.
I think they are a construction. And Kai's just, so if you're on the way to meet me, let's say it's me, for chicken wings at an English pub. I don't do that, by the way. English pubs are terrible at chicken wings. But on the way to driving to the pub, you see a ramen shop with your favorite color sign. Do you have a ramen shop? I see. So when did I see it? Right, fair enough. So the query, if I understand what you're saying, is the answer to your first question, do you have a ramen shop? No. Right? It's not your ramen shop. It's somebody else's ramen shop you've seen, right? When did you see it? Well, we're not sure. So was it last week or whenever it was? But I think that's time. Like, lots of things about memory are malleable, and they're just a bunch of opinions, really. And so this is why I'm really nervous when people talk about memories in rigid terms. I think it's very much a stochastic, I think it's the right way to use it, stochastic relationship, right? It's not about A or B. It's always some color in the spectrum, right? And time is, I think of time usually as sort of recent, not so recent, long time ago, right? And those are obviously very loose definitions.
Yeah, I do agree that memory is malleable. But actually recently I have a discussion with other people on this as well. Like, is it necessarily a good thing for AI systems to take the kind of attribute of human memory whereby we keep updating ourselves with maybe the current environment? Like, your memories tend to be meshed up with what you experience now. And let me just clear the screen. But one reason why I think memory is malleable is because maybe memory, we want to adapt to current situation. So basically, we want to make the memories more and more similar to what we have right now so that we can use it more. So that's one rationale I have for the memory malleability of, like, when we recall, we kind of mix it up with our current inputs as well. All right. That's why eyewitness statements, if you give it the right conditions, you can actually make them think of different things. Like, for example, the experiment of a car with like hitting another car in front. If you use the word, what speed was the car at when it bumped the car, people will give a much lower speed. If you say what speed was the car when it crashed into the other car in front, just the word crash could make you think of like window glass breaking and so on. So there was no window glass breaking in the video, but if the moment you use the word crash, people tend to hallucinate this glass breaking and it becomes as real as the memory itself. So one idea that I have about memory is that it could be used to adapt to the current situation. We lose out accuracy, definitely, but that means we can use this memory next time in a similar context. Okay, so are we meant to be perfect records of our lives? No, we are not. But the thing that I had a discussion about is that, do we want our AI systems to be like us? Like basically not have accurate memories. Okay, like if you are building rack systems on data, you probably don't want your memory to be malleable because you want accuracy for those systems. But that's also why you don't exactly trust a human to remember facts. We don't remember very well, but you want the AI systems to remember well. So maybe this kind of malleability may not be necessary to build in for such systems. But if you want the system to be like an agent like us exploring the world, then yes, maybe we build in this malleability.
I
Yeah.
think that's a good point in terms of what's desirable versus what's effective. Right? And for people, our memory is what's effective for people to evolve to where we are today. Right? And we don't know about the future because that's a different problem. Right? But and it becomes a mechanism for us to cope with our new environment. But we have in technology different ways of doing that. Right? We need a sort of I want to say a metaphor, but or a simile or something or other. We need something that has the same, be the architect for a minute. It has the same architectural function as malleable memory, which is focus on the present and the future. But the means by which we build that function doesn't have to be the same. So like with, you look at, say, transformer architecture, is that how neurons work? No, it's just not, right? Because we have different mechanisms to work with and different opportunities to optimize for. So we have something that behaves like a lot like a whole bunch of neurons, but in fact the underlying technology to give that outcome is wildly different. We're talking semiconductors versus biological cells, and so but with the result is similar enough. And I guess that's the thing. What's needed for this AI to have the same behavior to allow you to build for now and next. And I think part of it is I think this is like RAG, but not like RAG as well, right? So RAG is hit your knowledge, your fact base. RAG is built for the way we use it today. It's built for retrieve facts.
Yep.
But
retrieve the data, exactly.
But
yes.
yeah. So it's a straight up data retrieval, right? If then else, etc. The way we're describing memories here is much looser, and we'd probably, I suggest, retrieving capabilities rather than facts. But but it just feels like it's like RAG does what it does really well, which is great. But maybe this is a different. We reuse some of those that technology, but for a different outcome, perhaps.
Yeah, I mean, if you want to build adaptable agents, maybe what we can do is we can mimic what our brain does with our memory. We can mash up the memory in the database with the current state of the world. So that could be a new form of memory updating. In fact, there's some other things here that I didn't put in. Like you could have reflection over like long-term horizon of new facts. Like for example, this switch opens the light bulb and so on. You can have this kind of reflection memories, what went wrong, what went right. You can have new memories inserted based on your reflection of existing memories and so on. And all this can also be part of your memory soup. So it's very, very versatile. What is in the memory soup is up to debate. I think we should have a whole session on this to talk about this, because I think if we continue talking about this memory soup, we will finish the session without me covering the rest of the slides. But I do think this is something very exciting. I've never felt this excited about an idea since Fast and Slow. This memory soup seems right to me. So I'm very keen to pursue this, because I do think this is how memories might be encoded. I mean, previously I was thinking about how to encode it in hierarchy and so on. It's hard to encode in hierarchy, but if you encode everything into like this kind of memory soup where you put all into one space, and basically based on what you need, you extract accordingly based on your context. I think that is much easier to encode than a hierarchy. So I'm very excited about this memory soup idea. What is in the memory soup? Is it the actual memory itself? Is it the modified memory? Is it the reflection of the memories? I think all this we can discuss further. It will definitely depend on your use case, but I do think this idea of memory soup is correct. Okay, last comments before I move on to the next slide. Richard, you have anything else to add?
No, I'm good. Thank you.
The rest? Okay, so this method is quite new, quite exciting. Do stay tuned for it because I think this is going to lead to something impactful. Okay, I have good faith that this is the correct method. Right, so moving on to fast and slow. So this is what I'll be presenting like 2 days later at Macau. So basically, before LLMs became very, very popular, I came up with this idea at NeurIPS last year, December. And what I realized in like reinforcement learning is that, typically they use a neural network to model like value functions or reward functions. What I realized is that actually you just need to model the goal. Okay, you just take a current state and the goal, you just predict the next action. It performs way better than existing RL methods. And this goal conditioning, I realized something, is something like context learning. Because your context is like your goal. Like I want to eat ramen or something. That's your goal. So it seems that we don't really need reward. All right, that's one thing. Okay, but the thing that I'm going to talk about now that's more important for this session is memory. So over here, I use a parallel memory retrieval. Okay, and I sample various trajectories of memories that can reach the goal state, and I like choose the shortest one. So this memory helps us repeat desired trajectories based on the goal. And the good thing about memory is that you can learn this instantly. When you have a new episode that you store in your memory, you can sample and retrieve the memory. Okay, based on, I mean, the way that I store the memory here is state 1, state 2, and the action. So it's like a transition from state 1 to state 2. So if we talk about the memory soup idea, we can store various states, and state 1, state 2 need not just be a single time step. It can be higher time steps and so on, but all this can be all in the same soup. Again, then you just retrieve the soup accordingly and try to hit this goal, right? So the idea that memory can be used to do instant update of the way you behave in the world, it's very powerful. Okay, and the idea of goal-directed learning is also very powerful. So if you're interested, you can read more on this paper, Learning Fast and Slow. This is like my landmark idea. And I think with the era of large language models, it has exemplified this fact. Like context dependent learning is very powerful. So that's like goal-directed learning. The other thing is memory is also very powerful because memory is like your context that you learn from. So that is also something that it's very, very important in an adaptable system. Okay, so maybe this left part, the neural network, is not exactly context based prompting. This one maybe it's instruction fine tuning. Okay, because you have different instructions, and then it's like the goal. Let me just change this. Okay, it's context, but it's more like instruction learning. Yeah. So I do think this has a lot of parallels with the way LLMs are being done right now. And this idea of including the instruction and also including memory in the system, I think this is a very, very powerful way for us to create adaptable agents. So we are on the right track. Okay, humanity is on the right track here. Right, so let's talk a brief segue to hierarchical prediction. Okay, because this is something that a lot of people have talked about. Like, how can we potentially increase the accuracy of our predictions and over a longer time scale? Perhaps we do hierarchical prediction. Okay, so this is a study in Nature saying that like if people hear the words once upon a, they kind of predict time. Okay, this will light up in the human brain. Okay, and this one also will light up. So there's one component that talks about like a higher level component like time in, then this also lights up, and this one also lights up in the dark forest. Okay, I have no idea how they get the higher level components because as you go up the levels, you get more possibilities. So actually, it's very hard to model this unless you do increase vagueness. So the exact details of how they got this, I'm not too sure, but they have found elements of hierarchy inside the brain. All right, so maybe we do prediction not just at the base level, we do predictions at multiple levels. And if you can master how to predict at higher levels, you essentially make your prediction problem easier. All right, so for example, let's let's say I want to go from point A to point B. Yeah, I like to give this example, point A to point B. But it's actually quite difficult to go there. So maybe we can split this up into point A to point C, then point C to point B. And over here, what we can do is maybe we are doing walking for the first part here, and then we are doing like driving a car for the second part. And essentially, this splits our problem into two parts, and then we can use the context dependency, like basically walk. We can then plan out actions at the bottom here that are based on walking. And then down here, we can plan out stuff that are based on driving. So based on the top level, we can then plan out the various actions that are associated with the different things. So there's some merit to hierarchical prediction because you can plan at a smaller space at the top or at a more restricted space at the top, and then you can use whatever you plan at the top in order to condition what's at the bottom. So that's hierarchical prediction. Okay, so even Hinton has this GLOM architecture where he says that bottom goes to the top, top goes to the bottom. So you condition based on the hierarchy. Okay, I don't know whether it worked out well, but the idea of having a hierarchical prediction is something on a lot of scholars' minds. And I think for good reason, because we can actually do quite good planning from a more abstract view, a more high-level view, and then you keep going down to the more bottom-level view. Okay, so for a good time, I actually like this thing as well. Yann LeCun, in his Path Towards Autonomous Machine Intelligence, he also talked about hierarchy. He used the joint embedding prediction architecture, which kind of predicts in latent space. Okay, but the idea is he has this top-level action. Over here, he used model predictive control, which is like some form of like cost minimization. Okay, so this is like your high-level goal. And then at the end here, you have sub-level goals. And then right at the bottom here, maybe you have the motor actions. Okay, so this is the idea of hierarchy prediction. At the top level, you can condition the generation all the way at the bottom. I like this idea a lot. I just don't like the model predictive control because it uses backpropagation, and I don't think backpropagation can solve AGI. Backpropagation just suffers from a lot of problems as you go through multiple layers. That's why you need stuff like, you need gradient clipping, you need other techniques to like skip connections and so on to try to minimize the gradient like explosion or gradient vanishing. So I don't think backpropagation is the answer. Okay, but the idea of from top level goals conditioning all the way to the bottom level, I think that is great. Right? And this is something that we could try to model out in a system. Okay, especially for systems that hierarchy is clear to derive from. Okay, like for example, if you have like different like for example the traveling, different modes of travel, okay, this can be one level of hierarchy. And then you could have like different actions per mode of travel. This one could be another level of hierarchy. So if you can have your system that is derived into very, very fixed, distinct points of the hierarchy, this idea works well. Okay, it helps to simplify planning because at the top level, you just need to think of the most big things. Okay? However, I've been discussing this with Richard a bit or so. Like, I think creating this hierarchy is not easy. Okay, how do you know which level of the hierarchy? Can you self-learn the hierarchy? That's not obvious to me how you can self-learn the hierarchy because like there's so many ways to form the hierarchy, right? If you change your hierarchy, you change the action space and you have to relearn everything again. That doesn't sound right to me. And like I think it will work well for some parts of the system. But if we were to rely on hierarchy for everything, how do you form all these hierarchies easily? There's no clear answer that I have. If you have any, please let me know. But this hierarchy forming is really, I think, very structure dependent, and you kind of have to provide the structure beforehand. So it only works if your problem is quite amenable to structure.
If I can, just quickly, you talked before about how in the past I think you called it goal-based learning, right? Where things that have been achieved become goals that can be achieved, if that makes sense, right? If I understood correctly.
Yeah. No, so your past experiences, whatever you end up with as your final state, that can be goals. Yeah.
Exactly.
So you can use your previous memory to base off it to achieve a new goal.
And I think Yeah, and if you choose a new goal, right, which is we talk about curriculum and so on. So if you choose a new goal which resembles or consolidates previous goals, then you would end up implicitly creating the hierarchy. So I think it's not that it can't be hierarchical. I just don't think you can set out the hierarchy before you've built it, if that makes sense.
Yes, actually, I've been toying with this idea as well. I used to have a friend I met in Europe, named Shu Cheng. She does this thing called chunk-based learning. So basically, based on the statistical frequency of chunks, you group them together to form bigger chunks. All right, and I used to think that that may be the way to generate the hierarchy. So it's like based on how many chunks you combine, you get your hierarchy accordingly. I mean, let me illustrate with an example. Like for example, this is a cat. So let's suppose like this occurs very frequently. You could chunk them together. Yeah, of course, this is not how byte encoding works. I'm just using words to make it easier. You can form this is. Then, like for example, if a cat appears frequently, then you can form a cat. So is perhaps the way we form hierarchy is by statistical chunking of stuff together, and then like the hierarchy will be based on like at the bottom level how you chunk them. This will be the base hierarchy, and then this one will be the top level hierarchy, and so on. You can keep chunking to form higher and higher hierarchies. So for a moment, I was thinking this might be the reason, the way to get it. But the problem is that there's many ways to chunk things together, and then if you chunk things differently, you might get them in different levels of hierarchy. Like if you chunk this is first versus this is maybe there's a way to, maybe if you think of it this way, like this is maybe is something that should belong in this level of hierarchy as well. Okay, but because you don't have it here, you might have it at an even higher level, and it may not make sense because things in this level of hierarchy, you should have certain action space that is the same. If we just do chunking like that, you may not get the action space that is similar here. Like in the transport example, you want your action space at the top, maybe it's like modes of transport like car, taxi, or like walking. But if you just do chunking like that, you may not get it. Yeah, same thing if you learn through backpropagation, like your latent space to get your hierarchies, you may not get the right action spaces as well for each level of hierarchy. So it it doesn't feel very natural to me to like learn the hierarchy. Like the hierarchy more or less should be defined from the start. Like, but that isn't how we work, you see. Like we don't exactly know beforehand there's a car, there's a taxi, there's walking and so on. Like how exactly do we learn this hierarchy in our brains? That's something I haven't figured out yet.
Hey, John and Richard. Here's a quick, really very extremely deterministic phenomenon, like in our society, right? It's how you become a doctor. Okay, so you were drawing, there was a goal on top, right? The CS2 and 4. If that's the top goal of how you become a doctor, right? Right now, people have a very fixed formula, and it works. Like, people with 3 to 4 generations, and they're doctors, and they know exactly what to do. So with that example, can you walk me through this graph and like exactly how it will work? Like, how you can divide into sub goals. Is that like a pure reductionist view? Is like, okay, yeah, okay, how I can train someone to be a doctor?
To run with your example, Kai, I think there's a couple of tricks to it. Number one, step one, if in your example, is be the child of a doctor, right? Very hard to arrange, but if you can do it, very useful, right? So you have a teacher, you have a mentor from birth, right? You have whatever natural predilection is required to be a doctor, we hope, from genetics, right? So step one, be child of a doctor. Step two, and it's really important to set that context.
Okay, so where would that be? Be a child of a doctor in this graph.
That's the trick, right? That is the nature of actor 1 or actor 2. Is there's a context which is not seen here. It is the structure, the hierarchy itself gives you that context, right? That's why this is kind of the trick, right? People say anyone can be a doctor, work hard, blah blah. Not true, rubbish, not true. Right? Like, no, first things first, right? Be child of a doctor. Way easier, right? Way more likely to work. So, and so setting the context, super important. Next up, we know so let's assume we've got all that in place, right? Let's just assume that's true. And the top right corner is be a doctor. So maybe action for actor 2 is your sort of mid-level activity. It might be do good at school.
Your high school. Okay.
No,
So
school. All school, right?
All school.
Right? Be good at school. And the next action after that is when you're in hospital and you're doing your internship, whatever it is, be good at interning, right? Which is a whole different set of skills. If you've ever seen some young doctors, you'll see what I mean, right? So be wise. Do whatever you can to be wise. Understand that once you're out of school, there's a whole different set of rules, whole different set of behaviors you need to succeed, right? And so they're these mid-level goals, A, B, right? How do you do those things? Well, at school, number 1, do all your homework. Do it early, do it well, right? If you don't know how to do it, get your parents to help you or somebody else. Find a mentor who can make sure you do your homework well. But when it comes to things, and that's really important, you keep using that skill of doing what's put in front of you, even through when you're in work, right? When you're in the workplace, right? You still need to do the things that are given to you. You still need to do them well. But you now have a new set of tasks, which are things like watch the hierarchies and the politics at work, right? Make sure you don't upset the people who can ruin your career on a whim, right? Because they exist. They're out there. You can upset the people who can't ruin your career on a whim. You cannot get away with upsetting the people who are the senior doctors who can just go, I'm sick of dealing with you, piss off. Right? So you need to understand politics, right? And pragmatism. It's a long story, but one time I found myself actually not very unwell, but hooked into a emergency rooms sort of heart failure environment, which is a very strange place, I can assure you. And the young doctor who was dealing with me found an older doctor who said, I need that room. She had a very unwell looking lady there. And what's wrong with you? And I explained, and they went, yeah. And 2 seconds later, I was out of there. I was gone. And they did need that room. They did need to revive someone. It was really important. And the young doctor who was treating me, just out of an abundance of caution, had put me there, not realizing there's one of those rooms available. And if I'm in it, it's not available for people who are actually unwell, right? So that's what I mean. These are different things, right? The be good at school, be good at interning, do homework well, understand politics, understand rational pragmatism, decision-making, right? Be wise, or whatever it's going to call. So these become these activities which weren't that important and weren't low-level behaviors once upon a time, but they become increasingly relevant and increasingly the focus as you find different environments and different problems to solve. I'm not sure I've answered your question very well, Kai.
No, I really think that you brought up the crucial point, right? So John, do you agree with this a setup? Like, how would you, like, what kind of treatment would you do, like, for like in a medical school? It's very rigid, very deterministic, right? Yeah.
So I think this highlights the point that fixed hierarchy would fail most of the time, because, like, for example, do good at school could be a mid-level goal, or it could be a high-level goal. If it's a even higher level goal, then do good at school will comprise of do homework well. Do homework well will do like other things like read well and stuff like that. So like there could be do good at school at various levels. Like it could be at the second level, it could be at the top level. No, it could even be, I mean, it wouldn't be at action level because that's the motor actions, but even here, like the do homework well, actually the action that I'm thinking about right at the bottom of Jeff is like motor actions. Okay, I mean, Jeff Hawkins also mentioned, like in his 1,000 Brains, that actually at all neurons in the brain have a kind of motor output, which means that they can control the muscles directly. So it starts to question like how much of a hierarchy is really a hierarchy, because if you were to do a hierarchy like that, it means that your action space should be the same for each level, and it's increasingly difficult to maintain this action, especially when you view things at different scales. Like if you view school as your entire environment, then do good at school will be right at the top. All right. But if you view school as a subset of your entire life, then do good at school will be like in the middle. So it means that your different layers of your hierarchy would do different things at different points of time. And just insisting them to have a similar action space just from the hierarchy alone may not be a great idea, right? So I start to think that the hierarchy method, it might help to be useful for abstracting various abstraction spaces, but it's not the key method. Okay, so I don't know whether this answers whatever questions you had earlier, but I'm just saying that the hierarchy is actually quite flexible in some sense. Like your goals or your action space for one level might actually be the action space for another level in a different context. Do you understand this part?
Yep.
Yeah. So this idea of using fixed hierarchy, okay, it's actually like the knowledge graph thing earlier. Fixed ontology, it may not be applicable most of the time. It's rather context dependent. so I'm back to context dependent again. And maybe it'll be clearer in the next slide. Okay, so yesterday I went to read through on intelligence and the thousand brains theory again. So on intelligence was like the hierarchical temporal memory where you have hierarchy and a very, very fixed hierarchy, like what you see here on the left. Like this is how a ComNet convolutional neural network is normally said to work, okay, but it doesn't exactly work like that. Like first layer detects simple features like lines. Second layer, maybe you detect like maybe triangles. Then the last one you detect maybe objects like a coffee cup. So this has been shown that it's not exactly the case like that. Instead, what has been found out is that there are various abstraction levels or various reference frames, as Jeff Hawkins like to call it, of the cup. So you have one reference frame that talks about like the cup itself, maybe the front view, one is the side view, one is the tactile shape. So there are different ways to view the cup. Okay, all of them, okay, can be viewed at different levels. Okay, this is not exactly a hierarchy also. This is basically just the connections of the neurons that may form a hierarchy. So this might still be formed. Hierarchy might still be formed, but it's not an explicit action space per se or what. It's just like if you have different latent spaces at the bottom, like various latent spaces or abstraction spaces. Jeff Hawkins calls it reference frames, right? But essentially, it's just a way of viewing things. Like you just view coffee cup differently, like different views of the coffee cup, different sensory interpretations, and so on. It's just like different ways of transforming your embedding vectors, right, into a suitable latent space. And there's millions of these latent spaces everywhere. Okay, so what will happen is after you go through a latent space, okay, you might interpret it with a second latent space and so on. And basically at each point of time, you would know the whole cup as it is. Okay, there's no like subparts of the cup. There's no like, oh, I view the handle, then I view the mark and so on. Everything is one space. Right? If you only view the handle, okay, you would still be mapping into like a latent space here. So if, to put this concretely, so maybe this is handle and this is the cup. Okay, this is latent space 1. Okay, but there might also exist another latent space like that, where the cup and handle are somewhere else, like cup and handle. It might be very far away. So this may be latent space 2. And the thing is, we learn multiple of these latent spaces or abstraction spaces. Jeff Hawkins doesn't know how we learn it. My hypothesis is that we learn it through self-supervised learning. We predict something. Each neuron predicts something. Every single neuron is a prediction machine. We predict something. And I believe it's something like next token prediction of the action. I believe they predict the action given the start state and the end state, something like my learning fast and slow. Just that it's done at various levels of skills, various levels of abstraction spaces. Okay, we learn all these multiple latent spaces. Okay, it's something like one of my colleagues talk about slice mutual information. So it's like you have, let's talk about this. Like you have an orange here. Okay, we slice the orange into, okay, I suck at drawing, but let's say this is an orange. Okay, and then you slice the orange. This is layer 1, and then you slice it in a different part. You see a different part. So you can slice the orange in multiple ways. Okay. It doesn't matter how you slice it. As long as you have enough slices, you can tell 2 different oranges apart from one another just by looking at just the slices. Okay, because they are different. They are just different ways of mapping the space of possible things. So instead of just having one latent space, you could have multiple latent spaces. Okay, and each latent space, this latent space might also build on this. Like this first latent space might give you a big another latent space, so and so on. So there can be building of latent spaces, and that kind of mimics the hierarchy, but it's not necessary. You could just have 1,000 different slices of your orange, and you can still determine whether an orange is an orange or an apple. All right. If you slice it the same way, you view things in the view different latent spaces, you can do sort of understanding of how the object looks like by considering various views. Okay, and what I'm thinking is that all these latent spaces, okay, can actually fall in the same memory soup. Like this encoding here or that encoding here, we don't have to limit it to just the latent space alone. Okay, we can store everything in just one common pool of memory, like here, different types of abstraction or latent spaces. And then when you need it, okay, each of these cells, when they need it, they can then draw on that latent space that we have in that soup. Okay, because you do pattern matching, like cosine similarity, you will tend to take the latent space that matches what you are having right now. Okay, of course, this is just an idea. It's not tested yet, but it could jolly well be all the latent spaces all be formed in the same soup. So what used to be hierarchy is actually multiple abstraction views. And I mean, you can also have hierarchy building on one another, but all this also go in the latent space, go in the memory soup. And the beauty of this is that when we do planning, okay, just now earlier we talked about like going to school can be at the high level goal or the middle level goal. When we do the planning right now, it doesn't matter which actor is taking your actions. You can just extract based on your context. You can extract the relevant memory in your memory soup. You can do planning about being the best at school at any layer in your hierarchy, in the hierarchy model. Or in this model, any actor here can do the planning for doing well at school. Doesn't matter, okay? Because all they need to do is based on the context that they receive from the from the parent node, right? You are able to do the planning because you can just retrieve from this memory soup what you need. It's like this magic bag. Okay, if you need to do task A, you take out task A memories. If you need to do task B, you do task B memories. Okay, you don't have to have a constrained action space for each level of the hierarchy. So at the end of the day, you will have multiple models here, and you will just do some voting, maybe majority voting, to decide what object is. For example, if you want to decide whether or not it's a cup. And this is very similar to multiple sampling, and then like choosing the majority and so on. So I think this is a remarkable idea. I was mind blown yesterday, and today I was thinking about it, and I think this should be correct. Instead of having a fixed hierarchy, we have just have multiple abstraction spaces, and then we basically just do pattern matching to find what we need for planning. Okay, I'll open up like maybe 5 minutes for discussion here. I think this is a momentous slide to end on because this whole thing here is new. Okay, everything that I just talked about is new. I think this is quite revolutionary. If we can encode this out, okay, there could be a lot of possibilities that you can have. We can still retain the hierarchy model, definitely, but the way the hierarchy works, okay, the action space, all this is not constrained. The hierarchy only works based on the structure. Okay, but the structure is just defined by latent spaces and just doing self-supervised prediction at each latent space. So I think that is quite impactful. Like, any comments? Yep.
Looking at this, so what is if you watch me, what I've been up to on LinkedIn. So one of the things I've been playing with is an idea, like I said to you, the bias towards implementation, my background. And I think to implement this, it's going to much more closely, like one of the questions that comes up if you talk about implementation is so you want to have these memory spaces, great. How do you build that? How do you make it, right? So if you keep it in RAM, you will run out of RAM, or you will need an actual supercomputer, right? So, and that will eventually run out of RAM, right? Because our memories as people are actually vast. We're really efficient at cramming in more stuff, and it seems to be, my suspicion is it's related to rate of physical growth plus how, like your brain's a muscle, how much practice you have at memorizing more things, right? And something to do with those things comes together, you can memorize an amazing amount of stuff. Everyone can. The challenge, so therefore, you start to want a thing that looks more like a traditional database. Yeah, because by abstraction, I mean vector embedding. I'm using abstraction in a broader sense, like as architects, I work as an architect, that's my job. And we talk about abstraction. Probably the reference to understand that idea for architects is a book called The Architect's Elevator. And so you might talk about a low-level abstraction is a programming language. A high-level abstraction is the philosophies of different cultures, right? And they're all abstract, right? But in this sense of building these different spaces, they can be, particularly if you have this multimedia idea, right? And whatever. So all these things get fed in at the same time. And I do think it has to look like that eventually. So John, your comments the other day on Discord about lava and so these visual textual systems that are coming out recently, I think is really interesting, and having all these different embeddings kind of mashed together into this memory soup. And I think it might look like that one day, but that's another problem.
Yeah, I do think multiple abstraction spaces include multimodal as well.
Yeah.
Yeah, definitely.
But then, so once you get this idea, if you want to beat out just RAM, because that's a physical limitation, and we don't know how big this is going to get, it's going to get pretty big. The systems you start looking at things like Postgres and MySQL and what have you, right? And you want a thing like a database, and it needs to be, and there's nothing we've talked about here which can't be represented in a relatively traditional database system, right? There's, so you can, one of the real competitors, say, against Neo4j in the graph marketplace is just encoding graphs in Postgres, which is free, and it's probably I think it's currently the most popular relational database management system. But actually, there's nothing hard about graphs if you've got a relational database. Right? They're pretty easy, in fact. And somebody did a trivial one in Postgres and then benchmarked it against Neo4j, and it was pretty good. It was like, in terms of bang for buck, it was right there. And I think the same is, and people have already built vector indexes into Postgres. So now what you open up is a memory soup, which is terabytes, even exabytes in size, right? They can be proper big, right? Now, you also open up other challenges, but they, like, in terms of scale, they can be vast. And because of the way their indexes work, there's no particular constraint in how big the index can be or for the functions you can use to address it. So, although indexes imply functions, but that's another thing, right? And so if you look at the structure, then you can have, in a more classic sort of database representation, you might have the original source data, which is the bitmap if it's visual, right? Here's the bitmap. And then you have maybe 6 or 8 separate indexes of that data. One of them is keyed on color, one is on time, one is on whatever, but all of the metadata is present as well and separately indexed. Now,
you're talking about multiple ways of indexing your data, right? One on time.
Well, yeah, but there's no constraint. You don't have to have one, is what I'm taking a long time to say. You can have lots of them.
Lots of ways of indexing, and you can use all of them together.
Yep. And
that's right.
And I think that cosine similarity is just one. It's a really good, powerful one. But also then this idea of, we're talking about relationships and how they, here you have the 1,000 brains theory slide, and you've got these arrows all going back and forth between the objects. We all know they're very similar objects, right? Because they're all coffee cups in some representation.
Yeah.
Right? So, yeah. So there's nothing, I think, in my mind of latent space that means it can't have explicit relationships. Even like, particularly we have this idea of multi-indexing, right? You have an idea of a coffee cup versus the way it looks versus the way it feels, right? The way it feels is closely associated with feeling hot, because it often has hot coffee in it, right? But that has nothing to do with how it looks, right? So you need to make this relationship branches from visual input to tactile input, and that's because they have nothing in common otherwise. So maybe they just need more dimensions, and it goes back to your cosine similarity. But I like the idea of relationships, but maybe not necessary. It's just more dimensions.
Yeah, actually, you talk about index, right? If you think about a vector index, like a vector embedding, like perhaps this front part could be the index, like how you index it. I mean, the index could be different parts of the embedding. So it's like info. So maybe the vector embedding, like maybe the first 5 is index and the next 10 is info. That's for one kind of index. Maybe there's another index that the index is like towards the center here. So so based on where you want to index, like you can perhaps use some form of like priority to retrieve vectors similar to your index, but the vectors are all the same. You just change where you like focus on your.
And if you partition the index like that, you actually end up with functionally separate indexes.
Yes. So this is something like I had this idea called incomplete hash map, which basically means that you do cosine similarity only on a subset of the vector space. Okay, and this means that you can do various ways of viewing the problem using the same vector. Like you don't have to change the vector. Your latent space can all be the same, but the way you do cosine similarity will differ based on how you partition your vector. And I think this is very similar to what you were talking about index earlier. Like you can index by time space, or you can definitely just extract the time part, extract the space part, and then you can get the relevant memories just for that particular part. And you don't have to change the vector. You can just use the same vector. But parts of it, yeah. So I like this idea a lot because the incomplete hash map is the idea that I came up with to deal with multimodal memories. Like if you only see the audio, but you link to maybe the visual part, you have no info from the visual stimuli. But because of your audio stimuli, you can refer to your audio memories and you can link up to another memory that has the visual inputs that you need. So it's like sometimes when I hear particular music, I remember what I'm doing when I hear it. I don't have that stimuli of what I'm doing right now, but I can still retrieve that memory because I do an incomplete hash map, or I just retrieve only that particular section of that memory related to audio. And that's like the index over here. This index is what you retrieve. Okay, but after you retrieve based on index, like cosine similarity based on your index of the query to your memories, you will get the info for free as well after you retrieve it.
But maybe if I'm going to, so it's interesting. I like this idea. So if we run with it for a sec and go, I was saying like this multimedia challenge, right? Lava and so on, visual versus textual versus what have you. So what we might end up then is separate embeddings indexes that then are correlated into a common latent space. So if your index were visual, then the result, I'm going back to database build and design here for a second, so bear with me. What it actually resolves to is some vector in latent space, which is not in the embedding space. And that shared latent space would be shared with your text definition of coffee or a coffee cup or whatever you're going to refer to, right? And then you could have a common latent space, which would then have many things pointing into it based on different stimuli. But in and of itself, in principle, it would be complete-ish. This feels a little bit more like the sort of Jeeper approach of Lacoon, right? But where you've got or even the CNN in the classic view, right? Where you've got the initial and then a translation. But for mine, the trick is to do that, I don't know, as high up the stack as possible, as much time as effort is spent in the latent space as you can manage. And but that's the challenge, right? I'm not sure how it works.
Actually, it could be latent space all the way up, right? Like what the 1,000 brains theory is. Everything is latent space. It's just mapping to different, you can jump from one latent space to another. Like, for example, you retrieve memory of a place, you might link to the audio, then you retrieve memories of the audio. Just now I was talking about the chain of memories. The chain of memories could jolly well happen here as well. You from one memory itself, you retrieve what's the relevant one, you go to the next memory, and then you go to the next memory and so on. This could implicitly be a chain of memory as you go up the various levels. Yeah, so I do think that there's some merit to this view that you're talking about, like everything being in the latent space. In fact, that's how transformers process, right? If you look at the transformer architecture, everything is in the tokenization space, the vector embeddings. And then every time we do a query key value, we actually map it using an MLP to a different abstraction space. So the MLP could actually be sort of performing like a mapping to a new latent space or new abstraction space. Yeah. What is not currently done is this part here, this incomplete hash map idea. Okay, it's not currently done right now. I think this idea has some merit because it can split up the various modalities.
Yeah, I think that becomes a challenge, right? So I suppose that's because I like that idea of the different modalities is really important. I think it is. But the problem of breaking up your index like that is you need to understand what each part of the vector means, right? And that's not you don't really get that in latent space, right? Because it's unknown, because it's latent. So you end up with, and that's why I was suggesting to take, so that was my point of departure, to say, put the different modalities as separate indexes into the same latent space, because they all have their own embeddings for each different media type.
Okay.
Right?
So maybe the first 5 is touch, the second 5 is audio, the next 5 is vision.
Something
so
like that.
We do the incomplete hash map, we don't split the modalities, we just hash out some modalities.
Or just zero them out to nothing and run from there.
Yeah,
actually that's a fun idea. I like that.
Within the same modality itself, it could be possible to have different ways of representation as well.
Yep.
So the key thing is, how do these latent spaces coexist in this memory soup? If it's going to be the same memory soup, if not, it will have to be separate memory soups. But I quite like the idea of everything being the same memory soup because, that makes much more sense, because anytime any level here needs to reference that memory, it can. Okay, rather than it being tied to a specific layer of the hierarchy, I prefer the memory to be free flow, because then any layer of the hierarchy can do any kind of action. That will be the,
At an implementation level, you can reserve one value in the vector as being the modality, right? So this is mine. I know what this one means, right? So we cheat, basically, right? We impose a structure on one of the values in the vector. We only need one. We don't need a lot of them, right? Each value in the vector is 64-bit. That's massive, right?
Yep.
Or 32-bit. Doesn't actually matter. Like, you've got one's enough. And you use that to say, this is of modality X versus modality Y. This value is 0, that value is 1. Things which are less like that, we give them as distinct as possible values available to us. And that, in effect, partitions the soup but every element remains reachable.
So you're talking about a filtering mechanism to filter the soup.
Well, that's effectively what your hash map is talking about, right? With your
yes. Interesting. Okay, well, I love to continue the discussion. I think we kind of reached the time. We probably need a part 3 for this. I didn't expect it, but it's good. I like the discussion. Kai, you asked, don't we have the concept of clone structure of individual memory? Do you want to describe this? Because I'm not too familiar with this.
Sure. So you remember there was another user joined today in the Discord, and I don't know if it's like a he or she. I think they describe a paper called a clone structure graph representation for flexible learning. So if you,
I haven't read that paper yet.
Oh, okay. So the idea is that you can clone the memory, right? So once you create those clones can be like a copy of it, and they can form like a free structure, right? So all your memories over there, like 1, 2, 3, 4, 5, they can be cloned and then form a structure. So I think that's how they solve the problem, and they solve this problem also by cloning the learning from one agent to another agent. So that could shed light.
Transfer of experiences. Yeah, that'll be cool.
Right. So I don't know if that fits into the conversation.
I think the memory soup might be transferable between agents.
Yes.
Yep.
Yes.
But
then you can make a copy of the soup, right?
I want to say one short part. The transfer of the memory need not be complete, because I think if you transfer everything, you might cause a performance degradation at the other side of the agent. So there must be some smart way of transferring memory.
Correct. Yeah, that's the biggest problem.
Okay, if not, I want to before we move on to like maybe the last 5 minutes to discuss, let me just share with you, like, this will be next week, because I don't have time to, but this will be about agents and intelligence. I think this discussion here is quite interesting. We can talk about this next week, okay? But let's just end on this slide of the memory soup here. I think today we have discussed quite a bit of like how we can incorporate fixed rules versus flexible rules, and also like how we can use memory to improve performance and adaptiveness. And we talk about how it need not just be a hierarchy, it could just be a mix of different abstraction views. I think this is a very new idea, and Jeff Hawkins did mention it in Thousand Brains theory of intelligence. He just doesn't know how to create the reference frames or abstraction frames. And I think right now we are getting close as to how we can actually learn this through self-supervised learning, through just action prediction. I think we are hitting we might be close to solving this problem. Yeah, but how exactly to get these various reference frames? I still don't know how to condition it. I only know different modalities have different latent spaces or abstraction spaces, because like they just model things differently. Like if you look at the clip embeddings, there's a clip embeddings for images, clip embeddings for text. There are different latent spaces or abstraction spaces already. Okay, then it can be easy to combine them together, like in this Thousand Brains theory here. But for the similar modality, I do think for one single modality itself, like vision or touch or audio, there must be various abstraction spaces for the same modality. That I'm not too clear how to do it. Okay, so I will just end on this note for further thinking, because I think we haven't found the answer yet. But it's very exciting what the future holds for AI, because solving this problem will solve us more than halfway there to AGI. I'm quite sure of it. We need to solve this problem, and this approach is very promising. Okay, I'll end on that. Okay, 5 minutes for final discussions before we end the session. Anyone want to say anything else?
Oh, I was just thinking about the comment about clone memory and so on, structure. And I think that to me is very similar to what we're doing with foundation LLMs and then LoRa's on top of them. I think that's like we were talking about before, the capabilities of technology as opposed to biology gives us new opportunities. And that kind of cloning is not possible for biological systems today, or it is only for the fundamental structures through DNA and things like that. So we do have these new and different opportunities of perfect recreation that don't exist biologically. Now, well, that's actually interesting. Is that good or bad? Well, we'll see, particularly when it comes to AGI, right? Do you want a perfect clone of an AGI? Probably not. Like, evolution is useful for us all. And so that's a whole other conversation. But I look at, I don't think there's a particular issue with cloning. And I think one of the things that came up in Discord as well was this idea of, do you have one shared memory soup for all your agents, or does each agent have its own memory soup? And there's a bit of back and forth, right? And what does that look like? I think that's part of the multi-agent conversation. Are they really just clones of each other with a different context, which is how we use LLMs today? Or are they actually carved off and learning and separate to each other in their own private memory space? And there's good arguments either way. It's certainly not fixed by any means.
Yeah, interesting. I think we can discuss more on that. Of course, the answer to this is not easy. Okay, but solving this would be very, very important. Yeah. All right, the rest, do you have anything else to add before I end? Okay, if not, thanks for coming today. Unfortunately, we couldn't finish the slides, but it's okay because the discussion is more important. I think this part here would bring us more than halfway there already to AGI, as I said earlier. Yeah, and then the next part will be how to interact with multi-agents, which we will be talking about the next session. All right, and that's it. And see you around. Okay, bye.
Thank you.
Bye.
Bye.
Thank you. Great job.